focus on the acid dissociation constant. So we're talking about equilibrium within acids and bases. We'll go through both of those here today. All right, so the acid dissociation constant, when we were dealing with equilibrium, we just dealt with K. Now it's going to be called Ka because it is the dissociation constant for an acid, and then Kb will be for bases. So the equilibrium constant for a general equation, again, Ha is what we're going to use as our acid, a hydrogen bonded to something else. And this reaction that I have written here is one that's more realistic because this H and A are going to split up. The hydrogen is then going to bond to the water to make that hydronium ion. And then you'll just be left with A negative or whatever that hydrogen was bonded to as your anion. Then we can write our equilibrium expression. It is products over reactants raised to the coefficient of power, just like it was in the last chapter. We do leave out the water because it is a liquid, and liquids and solids do not enter into the equilibrium expression. Because of that, oftentimes we write the equilibrium expression for an acid ignoring the water. And we just say, well, the hydrogen's going to split off, and we all know it's going to bind up to water. But really, this is what's happening, and it is going back and forth. You would end up with a very, very similar looking Ka expression, except it would just kind of look like this. And then you don't have to worry about ignoring water because it is a liquid. And that's what this is all about. All right. So with this Ka, here it is again, and I showed you what it would look like without including water. We can write the expression for any acid, and you're going to find that they look like this all the time. You have your ions, what it splits up into on top, and then the concentration of the actual acid there on the bottom. Now, strong acids dissociate completely. There is no back and forth. There is no double-headed arrow when we're talking about strong acids because they split up and those ions do not get back together. So I'll show you here in a minute how to find the pH of just a strong acid, and it works the same for a strong base. All right. When we talk about those acid-base pairs, again, acid and the conjugate acid and the base and the conjugate base, strong acids are going to have a large Ka, and that's because you're going to end up, when that acid splits up because it dissociates completely, you're going to have a lot of ions running around. So you will have a lot of products. That makes a large K. And your hydrogen ion concentration is going to end up being equal to your acid concentration, as long, again, as it is a strong acid. We can look at that here in a question like, let's say I have a strong acid. Let's say I want to know the pH of 0.035 molar solution of the strong acid perchlorate. So what we're going to do here is we'll write the dissociation equation. KClO4 is going to split up into hydrogen ions and perchlorate ions. And then we can just use mole ratio. If this is 0.035 molar, then what is the concentration of the hydrogen ions? Well, it is a 1-to-1 mole ratio, so the concentration of my hydrogen ions is 0.035 molar. Again, because it is a 1-to-1 mole ratio and it is a strong acid. Notice no double-headed arrow here. Now, I was interested in H+. I don't really care about perchlorate because the question is about the pH. And I know if I have the hydrogen ion concentration, I have a formula for pH using that. So pH equals negative log of your hydrogen or hydronium ion, whichever way, ion concentration. So in this case, I'm going to find the pH of the solution. Take the negative log of 0.035 molar. And that's going to end up giving me a pH of 1.46. Again, in this problem, they gave me two sig figs, and the sig figs are located after the decimal pH, and that's why I went out to 2 decimal places there.
Sorry, what the stool is?
Now, weak acids, it's a different story. With weak acids, our Ka is going to be small. We're actually going to end up with more reactants than we have products because it doesn't give off a whole lot of ions, only a few. So the concentration of your hydrogen ions is going to be much, much, much smaller than the concentration of the actual acid. And to do those, we're going to have to use an icebox. A negative is a stronger base than water, and so it is going to push that reaction and gobble up the hydrogens and push that reaction back toward the reactants. Okay. Just a little bit more before we get into the math of Ka. Types of acids. We have polyprotic acids. We talked about this a little bit in Honors Chem. Diprotic acids. Now, protic means proton or hydrogens, so that means many protons. Diprotic is something that has two hydrogens available to be given away, like sulfuric acid. These two hydrogens can dissociate. Triprotic acid means it has three hydrogens available to be given away, and a good example of that is phosphoric acid, which is what is in your dark-colored sodas. Oxyacids, that's where we're going to have, actually both these examples up here are oxyacids as well, because they do involve a hydrogen bonded to a polyatomic ion, so you get oxygen in there. And the number of oxygens is going to have an effect on how strong the acid is. Organic acids are ones that contain carbon without it being carbonate. The way we can look at organic acids is you're looking for that COOH with the hydrogen is attached to an oxygen. It actually ends up looking like this. And then you probably have something else attached over here. That tells us it is an acid. It should look like acetic acid. And so when you see things that look like acetic acid in that COOH, then you'll know it is an organic acid. And this hydrogen right here is the one that is taken off to here as well. All right, now we know that we have our 6 strong acids. Everything else is weak. So let's get into how to calculate the pH of a weak acid. Now, these next slides, amphoteric, we talked about that, meaning something can act as an acid or a base. Water is a great example. Some of the derivations of pH, I kind of skimmed through when we talked about this before, but we did deal with these equations. Talking about water self-ionizing, producing both hydrogen and hydroxide ions. Each one was 1 times 10 to the negative 7. So when they are multiplied together, as in this equation, they equal 1 times 10 to the negative 14. So if you ever have hydroxide and you need hydrogen, you can use this equation here where they are equal to each other and use it to go from one to the other. If you have more hydrogen than hydronium, it's acidic. If you have more, hydroxide. If you have more hydroxide than hydrogen, then it is basic. And neutral solutions, they're going to be equal. pH, I went through, again, those types of calculations and sig figs. The only thing I didn't mention is this right here. We're going to get into that a little bit more, this idea of pKa, but anytime you see like pH, POH, it's the negative log of something. So pKa is the negative log of the acid dissociation constant, or that Ka, and we can use that to evaluate appropriate indicators, which we'll get into when we do titration, so hold off on that one. So then we have more relationships here that, again, we talked about before in the last little podcast, and our pH scale. Okay. Calculating pH of solutions, always write down those major ions. Talked about strong acids, how to find the pH of a strong acid. That's an important piece to remember because they do dissociate 100%. As long as we're dealing with a monoprotic acid with only one hydrogen, your hydrogen ion concentration is going to be equal to your concentration of your acid. All right, weak acids. Ka is going to be small. So it will be an equilibrium problem from the start. That's good. We're already warmed up with that. We need to determine whether most of the hydrogen will come from the acid or the water. There will be that competition there. Compare Ka to Kw. If Ka is bigger than all the hydrogens coming from the acid and not from the water, and so this would be the appropriate way to go about solving one of those problems. So I have this example. We have acetic acid, and they tell us the Ka. They also tell us the concentration of that acetic acid, and they want to know its pH. Well, a lot of this, the first thing you're going to do is dissociate it, because that is what acids do in aqueous solution. So I have my HC2H3O2. You could write it like that, or the other way. It's going to split up into its ions, and acetate ions there. And it is a weak acid because it's not one of those strong ones, so it will be going back and forth. I have 2.0 molar concentration of my acetic acid, and so that's going to be my initial concentration. Initially, I have no ions. That have not started, this thing has not started to ionize at all, and that's one of those little leaps that you're going to have to be able to make when you're doing these types of ice boxes with Ka and Kb. All right, so I don't know how many ions it's going to produce, and I'm really interested in hydrogen because they want me to calculate the pH, and I have a formula for H+. So I'm going to have that be X. This would be my change is going to be plus X. Now I'm going to move my change across the icebox. It's a 1-to-1 mole ratio, so this is also plus X. And you're going to find that that's going to happen a lot because you have one hydrogen and one cation and one anion, so they'll both end up being the same amount because it's one thing splitting up. This is going over the great divide, so this is minus X, and so it'll be 2.0 minus X. For our equilibrium concentration. All right, now I'm going to set this up into my Ka expression. Ka is going to equal my products over reactants, so H plus times my acetate ions over my acetic acid concentration. Alright, products over reactants, and now I'm just going to plug things in and I can solve for X. So they give me the Ka, and this is a pretty popular Ka for acetic acid. It won't be a bad idea to memorize that one. And then I'm going to fill in my equilibrium concentration. It's got to come from this part of the icebox. So X times X over 2.0 minus X. Now, from the last chapter, we saw that if K is small, we can make some simplifying things. Since K is small, X in relationship to other things is going to be so tiny that it's not really going to make a difference. So we're going to simplify and get rid of just this X right here to make the math a little easier. So I get 1.8 times 10 to the negative 5 equals X squared over 2. Then I'm just going to rearrange that equation. And I'm going to find that X equals 0.006 molar. That is my equilibrium concentration for hydrogen ions. So H plus equals 0.006 molar, and so now I can find the pH by taking the negative log of that hydrogen ion concentration. And if I take the negative log of 0.006, I get a pH of 2.22. Now I could find my POH by subtracting that from 14. And I could find my hydroxide ion concentration a couple of different ways. I could use that 1 times 10 to the negative 14 divided by my hydrogen ion concentration, 0.006, to find that. Anyway, I can go back and forth between any of those using those formulas that we talked about last time. All right. If you would like, I have this problem as well. If you'd like to pause this video cast, and then you can see how I worked it out. All right. So I got this one set up, and I have 0.22 molar of phenylacetic acid. At the beginning, I have no ions. I'm going to get some, though. How many? I don't know. Oops. Back one. Yeah. So that's going to be x. So our change is plus x. Then move your change all the way across. And here it's going to be minus x, so 0.22 minus x. Then we're going to plug that into our Ka. Ka is pretty small, so I can do that simplifying. And so that's going to be x squared, because hydrogen and the phenyl acetate ions are the same, over 0.22 minus x. Again, x in relationship to 0.22 is going to be too small to really make a difference, so we're just going to cross that out and simplify. Solve for x, and I get 0.0033 molar. And since x is my equilibrium concentration of those hydrogen ions, I can just take the negative log of that, and I'll get my pH of 2.48. Again, I left it as 2 sig figs, 2 after the decimal, because I had these 2 sig figs here.